Okay, let's look at geometric transformations. So we've already seen simple scaling, but let's look at maybe more general kinds of transformations we'd want to do. For example, we might want to rotate an image or apply some sort of warping or unwarping to undo lens distortion. A practical application would be to register two images such as satellite images of the same patch of ground. These are sometimes called rubber sheet transforms. So we're going to think of a transformation as a function that maps pixel coordinates. So let's say we have v and w are the coordinates in the original image and x and y in the transformed image. So for example, if we were just scaling by a factor of 2, then t is this function v over 2 and w over 2. But we actually need the inverse function because what we really want to do is go through the output image and figure out at each xy where that point came from VW in the input image. So one way to do this is to represent the transformation as a matrix. So let's take a look at a very general and useful transformation called the affine transform. So we'll take our coordinates, let's say u and v, and we'll append a 1 here. So it becomes a three-dimensional vector. We'll multiply that by a matrix, a 3 by 3 matrix of this form. So this is a affine transform because it has 6 variables in these positions and a 0, 0, 1 in the last column here. So this is pretty general. Can perform these types of transformations. Simple scaling like this, multiplying v and w times t yields this equation here. A rotation where we put a two-dimensional rotation matrix in the upper 2 by 2. We can also achieve translations by putting a translation in the lower row here. So that just adds a translation here. And we can do shearing horizontally or vertically or both. So that's actually a fairly general type of transform. How would you estimate those parameters? You can do that if you have a few control points or tie points. So let's say you have two images and you're trying to register them. And you know, let's say by hand or some other means, that this point VW should match this point XY. So those should be mapped to each other. And this point maps to this point, and let's say this point maps to this point, and so forth. So I have a set of points that correspond. So how many points do I need? I have 6 unknowns. Each point correspondence yields 2 equations, one for x and one for y. So that means I need at least 3 pairs of corresponding points to calculate the parameters of an affine transformation. So we actually want the inverse, so we'll just take the inverse of that matrix. And then finally, once we go ahead and apply our transform to find out the new coordinates, we go ahead and do gray level interpolation like a bilinear or bicubic. So 3 points I mentioned would be the minimum for an affine transform. To calculate the transform, you would stack your tie points in one image, x1, y1, x2, etc. here. In the other image, u1, v1, u2 here. So this 3 by 3 matrix multiplies this 3 by 3 by matrix. Or I can think of this as a matrix X. This is a matrix U and multiplying by T. So I can solve for T by taking the inverse of U on each side. So T is just U inverse times X. Of course, it's better to have more than 3 tie points, in which case you want to do a least squares fit. So stacking the points, let's say I n points up like this and n points up like this. Now I can't invert u because it's not square, so I need to multiply first by the transform of u on each side, and that forms a square matrix which I can invert. So I get the resulting least squares estimation of t as the pseudo-inverse is actually what this is called, of u times x. Here's an example from MATLAB, kind of a practical example. This would be an image taken from an airplane as an orthophoto, meaning that the airplane was looking straight down, the camera was looking straight down. So this is useful for map making. This is another image of that scene, maybe taken at a later date, but this is not necessarily an orthophoto. So this might be slightly not from vertical. It could also be rotated and scaled. So we want to basically find a few tie points between these two images and then find a transform that registers this new image to the orthophoto. And that way we could look for, let's say, changes in the scene, new buildings, new roads, things like that. So I'm going to use, there's a couple of useful MATLAB functions in the image processing toolbox. CP select, that stands for control point select, control point to treeform, and IM transform. Okay, so let me go ahead and I'm going to read in those images. Okay, so I have the two images read in. I'll go ahead and type CP select I1, I2. Okay, so this brings up a interactive tool where I can select tie points. So I simply click on each image. Let's see, I'll pick this point and this point. You want to find points that are easily recognizable and locatable. And let's see, how about this intersection here? I'll do one more. Maybe this one here. Okay, so now I have 4 tie points. I'll go ahead and save those. Okay, so I have 2 sets of points, base points and input points. So these are the XY coordinates of my 4 control points. So that point matches this one, this point matches this one, and so forth. Okay, so now I want to calculate a transform from those pairs. So I'll use the MATLAB CP to T-form. Input points, base points, and I'll say I want an affine transform. And the output is something called a T-form. Okay, so a T-form is a structure. And a structure, just like in C, has elements. In this case, it has these 5 elements. Let's take a look at the T-data element. So I can see what that is by saying tform.tdata. Okay, that's also a structure, but this structure has 2 3x3 matrices as elements. So I'll say tform.tdata.t. So that's a 3x3 matrix. Here's tform.tdata.t inverse, another 3x3 matrix. So these are the affine transforms of 3x3 matrices, one forward, one inverse, that I can use to register one image to the other. So to do that, I'll use the MATLAB IM transform. Okay, so it wants a image input. I think that's I1 T form. And we'll say bilinear is going to be our method. Okay. So that's going to create a, I'll call it I registered. Okay, so that applied the transform from the first image to match up the ortho image. So I don't have time here, but you can see it lining up by, if I just take the difference between these two images, you can see it's mostly black in this area. So it's not a perfect registration, but they are aligned. You can see how the roads align and things like that. In summary, to do a spatial transformation, we need to A, specify a function that maps points from one image to the other, and B, interpolate intensity values at non-integer positions. Affine transformations can perform rotation, translation, scaling, and shear. When performing the transformation to generate the new image, why is the inverse mapping useful?